but it shouldn't take you 45 minutes to do one part. So let me try and simplify this a little bit if I can. I tried the first time, but let me take another crack at it and see if it works any better. So did you understand normal distributions here when we were doing these? Did you understand how to do 6.1 and 6.2? Did you understand that?
6.1 and 6.2, I got done.
Okay.
So
when you're looking, okay, so just a couple of pointers just to ease us into this a little bit. So we can feel like we know something that we need to know, okay? Normal refers to the shape of the distribution. So when you see normal, I want you to think bell-shaped curve, okay? Bell-shaped curve. And that means that it's going to obey a lot of the properties of bell-shaped curves. It's going to be symmetric in the middle. It's going to be symmetric on both sides of the mean. It's going to have a peak at the middle. It's going to get flatter as you go out and all of that, right? So we think about the mean and we think about the standard deviation, right? So I'm going to try and get away from some of the notation for a minute. In 6.1, we're dealing with one individual member, I'll say, of the sample, right? One individual member of the sample, right? And we deal with, in 6.1, we're basically showing you what we call the standard normal curve, right? So we're showing you z-scores, right? That means that the mean, if you will, I'm going to call it the middle instead of the mean. You'll see why, because I want to compare it to 631. This is the mean in this is the mean in this section. It is the mean in 6.2 as well, okay? But I'm going to call it the middle. I'm just going to call it the middle because I want to make a comparison here because I think you might be missing that. The mean here is going to be mu, which is that thing that looks like a U. Okay. That middle is going to be, it could be 0, it could be some other number. Okay. But if it's the standard normal, then it's the Z and it's 0. Okay. It could be another number if you're on another normal curve, like if the mean is 100 and the standard deviation is 15, for example, okay? But if you're on the standard normal, it's going to be 0. Then we have the standard deviation. That's going to be...
When you say 0, you mean in the middle of the shape, right?
Right. So in this case, if we're on the standard normal, because there's a difference between the standard normal and a normal curve. Okay. The standard normal, that was a good question. The standard normal is a special case of this bell-shaped curve. The standard normal curve means that you're dealing with a curve where the mean is 0 and the standard deviation is 1. So sigma here is 1. Okay. That's what we're dealing with. So if you're looking at the standard, then so we did questions like this. We had 1 here, right? We had 2 here. And we had 3 here, right? And it would say, okay, they give you a z-score, right? So they give you a z-score. They'd say z is equal to, let's say, 1.28, right? For example. Yep. and they'd say, find the area to the left of this number, right? So you'd be over here and it would be like so. And you would say, all right, the area to the left is going to be something like this. You do here and you do something like that, right? You'd shade all that. That's the standard norm. Okay, my point though is that the mean is 0 and it's in the middle of this, right? And then we started doing, there were standard normal curves. These are Z's. Okay, these are Z curves. Standard normal means you've gotten a Z score. We also did curves where they were normal, okay? They were normal, but they weren't standard normal curves. So we also did curves like this. We did curves where we had, let me see. Where is my, I want to draw you, but where, okay, there we go. So for example, we had problems like this. We had, here's a normal curve. And let's say the mean here is 100. Okay, the mean's 100. The standard deviation is 15. So this is 115 and so on, right?
Okay.
This is 115 and then we have 130 and 145. This is 85, for example, right? And then she'd say find, it would be something like find the probability of X, notice it's not Z, X less than 85, right?
Yes.
And so in this section, you'd say, well, first of all, I'm dealing with, here's my 85 and I'm dealing with that, right? So this is going to be some other number. Now, this X less than 85, this is not a standard normal. This is not a standard score. This is my X, yes?
Yes.
So this curve is normal. It's not the standard normal. However, it has a mean. It has a middle score. The mean in this example that I gave you, the mean is in the middle and it's 100. Okay?
Okay.
Standard deviation sigma is the spread of the data and this is 15. Okay, this is 15. To do this calculation, I have to convert, this is called a raw score, in case you want to know the term. This is a raw score. Okay. I need to convert it to a standard score or a Z-score, same thing. All right, this is not a Z-score, this is a raw score. Okay, so X is our raw score. Okay, and we need to convert this to a Z-score. Okay, so we convert it using the formula here. Okay, so we need a Z. Now, Z, and then I convert it with my formula, Z. Now, this is a single, this is one person, right? Or one item or whatever. So this is, my Z is going to be X minus mu over sigma. You with me?
Yes.
This should all be reviewed, but I'm going somewhere with this. That's why just bear with me. I'm going somewhere with that. All right.
No, it's okay.
So this is my initial score. Now I have 85 minus 100 over 15. That's going to give me -1, right? 85 minus 100 over 15. I'm not going to get the probability right now, but I wanted to show you something. This is 15 here, so this is -1 here. Now, this is the probability of Z less than -1, right? Which we could get. Now that is a standard score, okay? You see that?
Once you convert it, like, and you get the
Right.
C-score, then it's standard norm?
Then it becomes a standard normal curve. That's right. That's right. That's how they're related. But the point that I want to make is no matter what kind of normal curve you're on, right? Whether it's a standard normal or just a normal curve, right? Where's the mean?
The mean?
Where is it?
We don't have it yet.
Yes,
Oh,
you
it's in the
do.
middle. Sorry.
Then, yeah, the mean is the middle score.
Okay.
The mean is the middle score, okay?
Yes.
So here's why I did all that rigmarole, okay? So normal refers to our bell-shaped curve. This is bell-shaped, right? This is a bell-shaped curve. Because that I will drill into your head until you're sick of me saying it. All right. And then the middle value is our mean. Okay. Now, when you get to 631, okay, so 6.2 is about 6.2 is about means, and it's about finding means of samples rather than means of single things, right? That's the difference. When you get to 6.31, okay, this is the central limit theorem for proportions, okay?
Okay.
Now, this is not a mean now. It's not a mean, it's a proportion. However, the distribution is bell-shaped.
The distribution.
The distribution is normal, okay? The distribution is bell-shaped and uses the same properties as you learned in 6.1 and 6.2. Okay? That's the connection. Now, there's one more piece to this. Okay? So what this means is that there's actually a couple of pieces to this, but this is how it's connected. So it's bell-shaped like so. Okay? But in 6.1, we had a mean here. Right? We had a mu there. In 6.2, we technically had a mean here, but it was called mu of x bar because we were talking about the sample. The mean of all the samples, which was the population mean, yes? So this is 6.1. This is 6.2 when we're dealing with samples, right? Now, when you get to 631, we have bell-shaped curves again. Here they are. Oops, not very bell-shaped. Let me fix that. But it's a bell-shaped curve, but we have a very important something that we have to check, because it needs to be bell-shaped in order for this to work. I told you that it's bell-shaped right here.
Yeah.
But there's a but here, okay? The distribution, let's try to spell correctly. The distribution of sample proportions, which is what you're studying in 631, is only bell-shaped if
Less than.
the assumptions are satisfied. That's why the assumptions are such a big deal. Those 3 assumptions that she has you test on every problem, that's why she has you test them. Because if they don't apply, if they don't work, then this is not a bell-shaped curve and you can't apply these techniques to it. Does that make sense?
Yes. Sorry, I'm just writing down what you're.
There will be wipe. I am recording this, by the way, because I figure you're not the only one with this question. So I'm going to assume that other people have questions about this too. But does that make sense why now she's having you do all this?
Yeah.
Now here's the thing. This was mu. This was mu sub x. This distribution in 6.3 is not a mean. Now it has mean, right? Because it's a bell-shaped curve, so it has to have a mean and a standard deviation, doesn't it? Because it's a bell-shaped curve. But it's not a distribution of means, it's a distribution of proportions, right? So the notation changes. The notation changes and it becomes this becomes the distribution of p's.
Distribution of.
Right? Technically, it becomes the distribution of p hats, okay? But they approach p, just like this mean in 6.2 was the distribution of x bar, but it becomes mu, right? That's what we're saying. Okay, so this is the distribution of p's. Now, if this is the distribution of proportions, you would expect the formula to be different, and it is.
Okay.
But the computations are similar. That's why, let me stop sharing this temporarily. And do I have, no, I have the homework. Let me stop sharing everything. And let me bring up one more thing from my files here. Let me bring up the slides for this so I can show you. Is this making sense now? Are you seeing a connection here?
Yeah, I went from like a 1, like 6.1 from one thing, and then like 6.2 was like the population all collective, right?
It was
And
all
then
the samples, right? All the samples, but we were doing means in 6.1 and 6.2, right? Now we're doing
then,
proportions.
yeah.
But what's the same is the way you do it.
Yeah,
Okay?
because I was able to write like what did I write down? I was able to get, oh, sorry, I'm gonna look back to my homework.
So if you
Like
look
the
at
P,
uh-huh.
didn't know where to plug what, and maybe it was just because I'm seeing the formulas with added P hats and P's and
Well, that's what I'm going to show you. So that's why I wanted to go back, right? So when you're doing, so when we're doing proportions, or when we're doing means, right? Let me share the screen here. Come on, screen. It's being kind of, I don't know what. All right, there we go. Here we are. This is the slide you want to pay attention to. Okay. This is the distribution. This is the same normal distribution. Okay. It just says we don't have mu now. We have P. You see? Mu of P hat is P. This is the middle. The mean is in the middle. The P is in the middle. Okay. And instead of sigma here, we have sigma of P hat, which is this formula here. Okay. So this is like 6.2 because you're dealing with more than one, right? So we have a proportion and we have our standard deviation, which we call the standard error, this thing here.
Okay.
Okay, you with me?
Yeah. Wait, is this multiplied? This sigma p hat equals this and then times that?
Are you talking about?
Yeah, right here on
sigma?
the bottom.
This is not multiplied. This is just telling you that this sigma refers to the sigma that's associated with the sample proportion. So
No,
the
the second part.
Oh no, this is just, this is a period. This is a
Oh,
period,
okay.
and then she's telling you that this root is called the standard error. It has a different name. No, it's
Gotcha. I was
saying
about to
that,
say
no, it's sigma. That's a good question too. I hadn't thought of that, but no, this is telling you that the sigma associated with p hat is the radical of the quotient pq over n, and the radical pq over n is called the standard error.
I got you.
Okay. Are we okay now?
Yes. I'm just writing down my homework. That
Yeah,
formula.
take your time. Take your time. No rush. We're here till 9 o'clock. If we need to be here till 9 o'clock, we'll be here till 9 o'clock. But I promise you we're gonna solve at least 2 problems before 9 o'clock, because it once you get it, it's not that, it's a little bit time consuming, I'm not gonna lie, but they're not hard. And all of the
because
problems are basically similar.
once I was able to get the rhythm of 6.3, I was able to finish the homework really fast, actually. Like yesterday, I was surprised that I finished 6.3, the part.
This is just a little more time consuming, but all the problems are similar in here. It's just there's a lot of detail. It's a lot of detail. Are you have any more questions about this?
No, we're good.
We're okay. All right. So here's how, in general, let me kind of back up the train here. Let me back up the train. Now, there are a couple of little nuances, not too many. She really didn't vary this homework assignment very much. So the way that this homework assignment in general proceeds is that before you start the question, okay, she's going to have you test the assumptions that you need to be able to use the central limit theorem for proportions. Okay. Now, why is that? I told you before. Do you remember why?
To see if it's a bell shape, like a normal bell shape.
Right. Because if these conditions fail, we don't have a bell-shaped curve and we can't do any of this.
Well, she adds something like that, and we'll just write no, it's not
Yes.
satisfied.
If you're doing the central limit theorem for sample proportions, she's going to say something similar. Are the conditions necessary satisfied? She's going to say that. There's only a couple of sections where she has you test assumptions. This is one of them because the assumptions are so important to the process itself. So you test the assumptions. There are 3. We'll go over that. Okay. You test the assumptions. Not always, she doesn't have you sketch the graph in every problem. I think the first 3 or 4 she does. Describe and sketch the sampling distribution. This is analogous to draw the normal curve, put the mean, in this case it's going to be the proportion in the middle, and then count the standard errors on each side. Draw the curve, just like you did in 6 point. You did this in chapter 3 when you were drawing the curve. Remember when we were learning how to draw 3 standard deviations in each direction kind of thing? That's this. And then you're going to find whatever probability she asks for.
Okay.
Okay. That's in general how it proceeds. Now, there's a little nuance to number 1 here in that there are 2 proportions and that can kind of mess you up a little bit. But did you have problems with the assumptions, or do you need me to go over that?
We can go over it. I had put yes, from like the PowerPoint, like following it. It says, does it have a number like on the PowerPoint, like if it has X, the PO hat, and then a sample size? And then there was a section, I put yes. And then there was something that she said, like, is it randomized? Yes. And then is it 10%? Rate 10%. So it is on this one, 25 and 33. So I don't know if I'm
did you watch the video that I created or not?
I watched some of it. I'm just still kind of lost.
Okay, no problem. I believe you, but let me just text somebody because they're looking for me right now.
ELT stratified.
So, okay, so here's the deal. First, we test the assumptions. Okay, so let's do that. Do you remember what the assumptions are? What's the first assumption that we test? If you don't remember,
I was trying to find a slide right now.
Let me give them to you. No, I'll give them to you. It's fine. Here they are. I was just trying to see if you remember, but here they are. They're on slide 10. Okay.
Okay, so the mean, the standard deviation, which will be the p hat, right?
Right, but don't worry about this yet. Okay, that's gonna come later. That's gonna come when we graph stuff.
Hold on, let me take mine off.
Before we do anything with the mean, the standard deviation, before we do anything with that, we have to make sure we have a bell curve in the first place, right?
Okay.
So the first assumption is we must obtain randomly obtained samples. Okay. Now this first assumption, you depend on the wording of the problem to tell you. Okay. You're not going to know otherwise. So you have to have some sort of wording in the problem that tells you that. So the first assumption here, so we're going to do number 1 together.
Okay.
We're going to do number 1 together again. We're going to do 1A. This is 1A, and 1A has 3 parts. Once you understand what they are, this is not hard, but like I said, it's a little bit of writing. So 1A, we're going to test the assumptions. What are they? Well, the first assumption is that the sample is a simple random. You don't have to write the assumption itself, but you do have to write if it's satisfied and why. Okay, I'm writing the assumption to help you. The assumption is the sample is a simple random sample. Go back to the problem here. Go back to the statement of the problem. It says, in a recent survey by a shopping organization, 33% of the 1,000 randomly selected, there it is. There's your statement right there. It says randomly selected Americans said that blah, blah, blah happened. Okay, this is stated. The only way you're ever going to meet this assumption is if the problem states it. Okay, so you have to have some sort of statement. Sometimes it says SRS for simple random. Okay,
Gotcha.
sometimes it says SRS. If you want to abbreviate it like that, you may do so. This is simple random, but there it is. It's stated. So you go back to your statement and you say, the sample is a simple random sample. You say, this is, so you put, you can, and I'm going to write a sentence just to make this clear. You don't have to write a whole sentence. You can write yes and put a check mark. I'm going to write a whole sentence just so it's clear. This assumption is satisfied because simple, or actually not simple, but random sample is stated in the problem. Okay, you don't have to write all those words, but as long as you say random sample stated or something similar to that. Okay, that's the first assumption. The second assumption is that, the second assumption is that the sample size is, so there's a couple of ways to state this. And so sometimes they state it with population, sometimes they state it with sample. The population size is at least 10 times as large as the sample size. That's our assumption. It's about size, okay? Now, the thing about this is, here's the tricky thing about this that trips students up. You have to know, you don't have to know the size of your population, but you have to know what the population is, okay? What group are we referring to here? So in a recent survey by a shopping organization, 33% of the 1,000, now this is where the 1,000 becomes important, okay? This 1,000 here, becomes important because you have 1,000 people. This is your N, as you said, okay? We'll get to the P's in a minute. We'll get to that in part assumption number 3. This is my N. Who am I surveying? I'm surveying Americans. okay? And I'm surveying Americans who shop specifically on Black Friday, but I'm surveying Americans, okay? So I have 1,000 people in my sample here, right? So the question I have to ask myself, and this requires going outside the problem, but it's never significant, but it does take a little bit of going outside the problem to ask yourself this. So the question I'm asking is my population ten times larger than my sample? Well, what is my population here? My population is, now you could say it's all Americans, you could say it's the number of Americans who shop on Black Friday. Doesn't really matter too much, but I'm going to say that the population is Americans, right? Just Americans, because that was what was in the problem. And my sample size is 1,000, because they told me that. That's in the problem. Again, the sample size will be in the problem. Any questions about this so far?
Yes. So when I did it on with going with the slides, I thought comparing it from the 1,000, like that would be the population, and then what we would compare it to would be the percent of what she was asking. Let's say, for example, the 33% or the 25%. Like, is that
Not yet. That you're thinking of part 3, but that's not here. Okay.
Oh, okay.
But that's a good, no, that's a good question, and I'll show you that. Let me show you this. So let me come back to this part right here. Am I sharing I don't know what I'm sharing right now. Let me share these slides. So each sample must be less than 10% of the population. So if you look at her example, let's come down. Number 2 is the 10% condition. So let me take you back to Concordia here. Here's 45, right? There's my sample of 45 people, right?
Okay.
There's my sample of 45. My population is students at this university, Concordia, right? How many students are at Concordia?
Way more than 45.
Yeah, the point is we don't know. And the reason I ask that is students get this confused all the time. They're like, but I don't know what the population is. Okay.
Yeah.
This is a common sense hypothetical kind of question. Okay. So what you do is you say, you look at the sample size here, 45, right? Multiply it by 10, you get 450, okay? So 10 times the sample size is 450, okay? Now you ask yourself, is it likely that Concordia, this university, has more than 450 students? Yeah.
Yes.
I mean, Cerritos College is a community college and we have thousands of students. So unless this is a tiny university that just got founded and they have, their first graduating class, maybe not. Concordia happens to be a pretty widely known school and they have way more than 450 students. So yeah, your population here, your population of all the students at Concordia is way more than 450. So your population is more than 10 times the sample. That's why I had you multiply this by 10. Your size of your population, even though you don't know what it is exactly, it's way more, as you said, way more than 10 times the sample size.
So it's 10 just like kind of just to compare them, like, oh, like just to
No,
look at like,
there's a reason for the 10 because look at the assumption. The assumption says each sample must be less than 10% of the population. So think about this. This might be what tripped you up. Think about this.
Yeah.
Let me do this on another whiteboard over here. Okay.
Yeah.
Let's say my whole population, this is my population here. This is my population. Okay. My entire population is 100%, isn't it?
Yes.
Because a whole would be 100%, wouldn't it?
Yes.
Now, if my sample size is 10% of this, right? So let's say that my sample size is 10%. So that's 10%. And I have another 10% and another 10% and another 10% and another 10%. How many of these 10% do I need to make 100%? 10 of them, right? So my sample size, and I'm just going to put etc. here, but my sample size should be no more than 10% of the population, right? So to establish that, I have to take 10. Now, if I take 10 times, if I take 10 times 10 times 10, where's my times? There it is. 10 times 10%, what do I get? 10 times 10 is 100%, isn't it?
Yeah.
So 10% of 100 is 10. That's why I'm multiplying by 10.
Okay, got you.
That it's a way to establish that. The other way to think of it, is to think, okay, what do I think the population of Concordia is? What do I think it is? Maybe I think it's 10,000 students, right?
Okay.
So let's say hypothetically, right? Let's say that you think the population of Concordia, because we have about 10,000 students between online and whatever. So you think it's maybe 10,000 in theory, right? 10,000 people, right? What is 10% of 10,000 people? You can do that with your calculator. Not quite. It would be 1,000, right? 10% of 10,000.
Oh, 10,000.
Right. 10% of 10,000 would be 1,000 people. Right. Now, that's your sample. That's the maximum, right? This is the other way to think of it. But I think it's harder to think of it like this. This is the maximum size of your sample if your population's 10,000 people, right? So this is the maximum size of your sample. You only sampled, in your case on part A, you only sampled 1,000 people. So you'd be okay. This is your, right? But there's more than 10,000 Black Friday shoppers.
Yes.
More than 10,000. You see what I mean? So you can think of it either way, but I think it's easier to just take the sample size, multiply by 10, and ask yourself, do I think the population is larger?
Okay.
Okay. But that's where we're going. Does that make sense now or not?
Yeah.
Okay. So are we good with, can we believe that maybe that okay, so I can say, this is part of my second assumption. I can say that this assumption is satisfied because, because the number of all Americans is greater, right, than 10,000 people, right? Which would be your 10 times your 1,000, right? The number of all Americans, and I'll say who shop on Black Friday, who shop on Black Friday is greater than 10,000. Are you clear with that?
Yes.
Does that make more sense now than it did?
Yeah.
So we've done the second assumption. Now the third assumption is the mathematical assumption. And it's usually the easiest, but it's usually the one that's violated. If it's violated, this is usually the one that's violated. The trick here is that this particular problem isn't as clear as some of the rest of them are about which proportion is which, okay? Because they actually gave you two, and not all of them do that, okay? That's why I did this problem specifically, because there are two, and I thought it might confuse you, all right? It says, in a recent survey by a shopping organization, 33% of the 1,000 randomly selected Americans said they were planning shopping on Black Friday. That 33 is from the 1,000 people, right? You see that? So we have two proportions here. Stop and think about that. We have two proportions here, don't we? Because this 33 if I can find there we go. This 33 relates to this 1,000 people.
Yes.
And this is my sample size, right?
Yes.
So guess what? This must be my sample proportion. This 33 is my sample proportion, isn't it? 33% of the 1,000 people in my sample said that they were planning on shopping on Black Friday. Okay?
Okay.
But in reality, only 25% of people actually did shop there.
Okay.
Okay. So when we do that, this is the percentage. We don't want to use this sample percentage. We want to use this 25% to test my assumption for part A.
Yes.
Now, there's reasons to use the 33, but not in part A. Okay. Not in part A, because, let me take you back. Here's my we're on the third bullet. We have arrived. Notice in here, you have the sample size. This P doesn't have a hat on it, does it?
No.
And this Q doesn't have a hat on it. These are population percentages, okay? So this is the population, this is your 25% in this case, and your 75. Okay? Questions about that?
NP, you said that would be 25 and 33?
Not 33, no. I said that you don't use 33 because that's the sample proportion, is what I said.
Okay.
Because your assumption here, let me write it. Your assumption is you're gonna test the products. Okay. And so we
Okay.
have to test NP. Can you hear me?
Yes.
Okay.
NP.
NP should be greater than or equal to 10. And these both have to work. If they don't, then it doesn't. So this is a two-part assumption and you have to satisfy both. Okay, so NP and NQ. Now, notice I'm going to write this on here. P and Q come from the population, not the sample. Okay, not the sample. NP and NQ. All right. So in this case, you have N is 1,000 because we beat that into the ground earlier. P comes from not the sample proportion, not the 33%, but it comes from the 25%. 25%, which is 0.25, right? Remember Q, go ahead.
1 minus 0.25.
That's beautiful. Q is 1 minus P, which is 1 minus 0.25. I feel your momentum is coming.
Yes.
So what is this now? This is 0.75. Let's test this, okay? So P times Q, so this is going to be 0.33. I mean, sorry, I ignore what I said. 0.25 times 1,000, which is what? That's going to give us 250, right?
Yep.
Now, that's greater than or equal to 10. So that's a yes, but remember we need 2 yeses, right? So now let's do Q. So we're going to do 0.75 times 1,000.
Okay.
What does that give us?
I don't know, sorry.
Should be 750.
Okay.
Any questions about this so far?
Oh, it's going good.
Okay, so now we've satisfied the first assumption. We've satisfied the second assumption. So I'm going to write a sentence. You don't have to, but I'm going to write it just to be clear. So since both products are greater than or equal to 10, greater than or equal to 10, this assumption is satisfied. Now, guess what? I've satisfied all 3, right? Have I satisfied all 3 assumptions?
Yes.
So then I say, because there's an answer to part A, and I'm going to put this in red
Okay.
to make it stand out. So I had to test the assumptions, right? You don't have to write the sentences. I'm doing that so that you'll be able to follow. But remember, the question she asked is, are the assumptions satisfied? So what you do have to write at the end of it, after you've tested it, you have to write something like this. Yes, the CLT or sample proportions applies in this situation because all of the assumptions are satisfied. You can write, yes, the CLT applies, provided that you show all this work. And yes, for those of you who are watching and will ask me, you do need to show this work. You don't need to write all of the sentences, but you do need to show that you tested them. You do need to show how you tested them, okay? So this is a lot of writing and this is time consuming, but this is how you do it.
Awesome.
Okay, are we good with part A now?
Yeah, that's more clear. Way better now.
Better now, okay. Well, I'll take clearer. It doesn't have to be crystal, but I'll take clearer than it was. That's cool. All right, so that's part A, okay? So guess what that means? What does that mean? Because I asked you, let's see if you can remember. Why did I need to do all this?
Damn.
I tested the assumptions, and because it applies, that means that what?
It's a bell shape.
That's exactly right. That means it's a bell-shaped curve. And if it's a bell-shaped curve and I can find the middle and I can find the spread, then I can draw it.
Perfect.
Dun, da, da, da. Okay, so now let's do this. See, this is how it's connected. And I want you to see that this is what you were missing. So now, see, now you fit the bell curve, right? So now we're back to this. The distribution of proportions will be approximately normal because the assumptions work. Do we know what P is?
Yes.
What is it?
Hold on. 12.5.
It's 0.25, right? Now, do I have a formula for the standard deviation?
Yes.
Yes, if you don't remember, I'm showing it to you on the screen. It's right here. Square root of PQ over N. Again, these are populations, so you're going to use 0.25 and 0.75 over 1,000 for this. Okay,
Gotcha.
I'm going to use that. There's a time to use the sample. We're going to get there. We're not there yet. Okay, this is population numbers. Okay. So once we get the mean and the standard deviation, we can draw the distribution, right? So let's do that. Let's come over here. You sound scared again.
No.
All right, so we're gonna go over here. We're gonna draw our well, we're gonna write some stuff out. Okay, so mu of p hat. So the mean of all of my p hats is gonna equal p, right?
Yes.
This is my middle, and this is my, remember, this is my population proportion, which is 0.25, okay? We just used that a minute ago. That's 0.25, right?
Yes.
Now, the other, we have a formula, but we haven't calculated. So let's write the formula. This is, you've used harder formulas than this. Okay?
Okay.
sigma of p hat, this is my standard deviation essentially. It's called my standard error for a reason, but it's essentially my standard deviation. This is the square root of p. Remember, this doesn't have a hat, so it's a population proportion. P, Q, N. Okay, do I know what P is?
Yes.
What is it?
25.
0.25. What's Q?
Q is 0.75.
Q is 0.75. Just like you, if you forget, you can get it from your assumption step 3, because you tested this product there. And N is what?
1,000.
Yes.
Okay, let me put that.
So we're going to stick all that in the formula. Now, because I've done this problem repeatedly, I happen to know that sigma of p hat should be 0.01 if you get it correct.
When I put it in the calculator,
Uh-huh.
I'm gonna put second, and then the little x2 to get that little the sign, and then I put them in parentheses.
The square root. Okay, let me show you that, because that's a good thing to know. Let me bring up the calculator here and I'll plug it in.
Okay.
It's taking a minute to open, so just bear with me for a minute, but I'm still here, folks. So this is, okay, let me clear this out. So now
Okay.
we have, I'm going to bring this up so that I can read my calculator screen. So I'm going to do, for my calculator, my square root is on top of x squared in the left-hand column. So I have second square root, okay? You can use parentheses, but you don't have to, because you're going to be multiplying p by q anyway. So this is 0.25, this is my p, times q, which is 0.75. Now, order of operations, it's going to multiply before it divides by anything I put in. So again, you could put parentheses, you don't have to, because it's going to evaluate it properly. This is 1,000, okay? For those of you who don't have the automatic extending radical, okay? For those of you that just have the root, remember that everything is under the radical, okay? So make sure that everything is under the radical. If something is missing, you're going to get a different answer, okay? So make sure it's all there. Then you get this, okay? Now, important observation here. When you're doing the graphing, 2 decimal places, because you're not going to be able to distinguish 0.0137 on the graph from 0.01. Nobody has graph paper that fine or eyes that good, okay? So for the sake of graphing, round this to 0.01. For the sake of what we're going to be doing later, keep 4 decimal places. So this is 0.0137, okay? Write down 0.0137 on your paper for your sigma of p hat. And for graphing, you're going to use 0.01. Gotcha. So we're going to write, and this will become clearer when we get there. We're not there yet. So just hang in there with me. We'll get there. Okay. But that's just something to be aware of. So we're going to say that sigma, and I should have, before I did the text box, I should have written it. So let me write it here. So sigma of p hat, we're going to say this is equal to, we're going to approximate it first with 4 decimal places. So this is 0.0137. We're going to use this for calculations, which are going to come later. And we're going to use equals 0.01 for graphing, okay? For graphing only, okay? Because nobody wants to sit there and try to find 0.0137 versus 0.01. We have better things to do with our life and our time. So now we know it follows a bell curve. We know what the proportion is. We know what sigma of p hat is. Now for the, hopefully, the easy part. This should not be the hardest part of your life. You've done this before. You've been doing it since chapter 3. Here's your bell curve. Here's the middle of the bell curve. Here's 3 standard deviations on each side. This should be looking very familiar to you. Here it is, right? This should be looking really familiar. Here it is. What goes in the middle?
0.25.
Right. That's because that's your mean, which is your proportion now. That's why I was telling you, remember when I was telling you the proportions in the middle, just like before? This is why I went over that. 0.25 right here.
0.5. So then I'm gonna do 3 of them and then just move it.
How
it'll
much
be
is each one? How much is each one? 0.01.
Point,
So what
so
is this
point-
going to give? Point what?
26.
26, then 0.27. And then now some of them are a little harder to add. So if you need them to, if you need it on your calculator, then by all means. This one happened to be easy to add. Some of them aren't. So feel free to use your calculator to add it if you need to, okay, or subtract it. So this is going to be 0.22, just because I've done this so many times. 0.23 and 0.24. Okay,
Gotcha.
now yours will be a little neater than mine because I kind of ran out of room. That's your standard, that's your distribution.
Yeah.
That's
Mine
part
looks
B.
nice.
That's part B. You're done. Any questions about this?
No, it's more clear now. Like now that you put the me, I always forget their names, but
This
the
is called mu of p hat. I'm gonna give you a little secret. So this mu is from the Greek alphabet. That's why it looks weird. It's pronounced like mu. Okay.
Yeah.
What a teacher friend of mine used to call the sick cow letter. It's not moo, it's mew, mew. They're mewing. They're a sick cow, so they're mewing at you. But this is the name of the letter, okay? So that's your distribution. Now,
Perfect.
now we're gonna go back to our, we're gonna share the screen first, though, because we didn't do that. Let me see. I did share the screen. I just didn't move the screen share. All right, so now we're on part C. What is the probability of selecting a random sample of 1,000 people and getting 33% or more saying that they shopped on Black Friday? This is where this gets easy. You're going to say, thank God, something easy in my life. As long as you understand 6.1 and 6.2. If you don't, then it might not be as easy. A random sample. Remember I said we're going to get the 33 back. This is my sample proportion now. I need it.
Yeah. So
See it?
I got this I didn't even check if the homework was right in the back, but I got sigma p equals, and then the square thing, 0.33 times 0.67.
No. You don't need to do all that. You don't need
Okay.
to do all that. That you're creating another, no. What we're asking here is you're on this distribution, right? So you're on this curve right here.
Okay.
Okay. So part C is you don't have to draw this. If it helps you, you can draw this for every letter. You don't have to. But you do have to draw it when she says draw. Okay. But if it helps you, this is what's going on. This is 25, right? And then you've got a bunch of stuff here. This is 26.
27.
And then you've got 27. Right? I'm just going to go here. And then you've got like some stuff out here. This is 22. This is 23. This is 24, right? So you've got that. Now, you're out here. This is your distribution. And I'm probably going to have to redraw this because I'm not going to end up where I should. Sure enough, I'm not going to end up where I should, but I'm going to fake it till I make it. This is, that actually wasn't as bad as I expected. I need the peak to be there, so we'll assume. Now, 33 is going to be somewhere out here. Okay?
Yes. Okay.
33 is way out here. Okay? So there's 33. Now, this is just like area under a normal curve, just like before. So what we have now is it says, what is the probability of selecting 33% or more? Okay, well, if we go back to this, oops, apologies. If we go back to 33% or more, we're in here, aren't we?
Okay.
Now, this is a normal distribution, isn't it?
Uh-huh.
And we know how to find areas under normal curves, don't we? Now here's the deal. Here's the deal. Just to remind you, we know, because I do have to remind you of this, because this is where the method, it won't mess you up, but you have two ways of doing it. Mu is 0.25. Okay? Because this is not a standard normal. This is a distribution of proportions. So our mean is here, right? And remember, when we use calculations, we're going to use our 4 decimal place approximation for sigma of p hat, right?
Yes.
So this is going to be equal to, 0.0137, right? Now, only for this section. This is a time saver, but it's also because of the properties of proportions, okay? You can convert this to a z-score. You don't have to, okay? You don't have to. She's not requiring you to convert to a z-score. So I'm going to write this on the screen so that people who are watching, y'all can come for me later, okay? But don't say I didn't tell you. She told you also if you were in class. Professor Nickdell stated in class, and it's also, I think she put a slide if she revised the PowerPoints. She said she was going to put a slide in it. Stated in class that she prefers if students substitute directly into the calculator without, this is big, without converting to a z-score first, just because this is already time consuming, okay? This is already time consuming and you can do it, well, but only for this section, okay? Only for this section. So that's there for you. Now, the question is, how do I do it? Remember the format. I'm going to give you the general format. This is the same format you had in 6.1 and 6.2. Normal CDF. I'll show you where to go. Okay. Normal CDF, your left bound or your lower, I like to call it left, but sometimes I call it lower, your lower boundary of your region, your upper boundary of your region, your upper boundary, your mean, but it's not the mean here. So this is going to be your P in this case, because that's going to be the mean of your distribution, and your sigma of P hat in 4 decimals. So this is going to be sigma of P hat right here. Does that make sense now? Because this is your mean is your proportion, and your sigma of P hat is your standard deviation. Does that make sense?
So I put.
So what it looks like for this problem is this. I'm going to bring it up on the screen. I'm going to share the screen again. So we're going to go to second distribution, like we always do. Normal CDF, make sure you're using CDF for this. Your lower boundary here is 0.33 because we're doing 33% or more. Your upper is E99. So remember to get your upper, you have your upper is going to be second E99. Your mean here is not your mean, it's your population proportion. So it's 0.25. And your sigma is your 4 decimal places, 0.0137. Okay, that's your sigma. Okay. Paste it and then do this. Now, this thing here is way small. Some people think, oh, my probability is 3.5. No, it's not. You have e to the negative 11 over here. And I have an extra, hold on. I have a different digit because I just made a typo in here. And I see it right now. Let me fix it. I have a 0.0137 in front of my normal. So I have a different number than I should. So let me do it again. This is second distribution. Hold on. Second distribution, normal CDF. This is all correct. It was just I had an extra digit in front of it. Here's my number. Okay.
Yeah, that's what I.
Now this is still 2.62 E negative 9. This is anything higher than 1, you know, is not a probability. Look over here to see what your exponent is. Okay. This means there's 9 decimal places to the left of where it currently is. That means there's 8 zeros. So you'd have 1.1, 2, 3, 4, 5, 6, 7, 8. Then 2, 6, 2, 7, 5, 8, whatever. All right. That's your decimal. Okay. So super, super tiny, right? You
Yes.
could round this to, you could write these zeros and then write a 3. But if she asked you to round to 4, you'd get 0. We're so far
Okay.
out. We're so far out that there's like virtually, there's a tiny bit of area, but it's negligible.
Okay.
And if you think about it, before you say, well, how is that possible? Look at, if you look at the distribution, let me show you something. If you look at the distribution here, your mean is 0.25.
Yeah.
Your standard deviation is 0.01. You're 8 standard deviations away from the mean. You're 8 standard deviations out. Remember, 99.7% of the data is within 3. So by the time you get to 8, you're out in, there ain't nothing out here, right?
Yeah.
And that's what it's showing you. So you have a tiny probability there.
Yeah.
Okay. So
Gotcha.
So what I would do is I would say probability of p hat greater than 0.33 would equal this normal statement over here. This would equal this normal statement, which would equal, and I can put, if I'm going to 4, then I'm just going to say that this is 0.0000, because I could go and write, but it's, yeah, it's small. Okay.
Gotcha.
Now D works. D works the same, except D has a different,
At most.
D has a different situation. It's written a little different, but the essence of it is the same. So D is, if I get back to my problem, what is the probability that most 190 of those 1,000 people shop on Black Friday? Now, in this case, she didn't give you a percentage, did she?
No.
See that? So you have to get a percentage first and then do what we did. So here what she did is this. Look at the slides and you see that that's why she gave you this. Let's come, there we go. If you look at this, she tells you that p hat is x over n. Okay. In this case, it's 190 people out of 1,000. Right? So my p hat here is going to be 190 out of 1,000. Go ahead and divide that. And we'll do part D.
0.19.
Right.
Oh.
So in this
Okay.
case, it says, that's right, that's your p hat. So now it says, what is the probability that at most 190 of those? So here, we're going to go back to our, distribution. This is part D of our, okay, so in this case, again, you don't have to draw this every time, but I'm just doing this for clarity's sake. We still have 0.25 in the middle here. This is 0.25. In this case, we have X is equal to 190. N is still 1,000. If I divide, I get P hat. All right, so I end up with P hat is equal to 190 over 1,000. This is 190
0.19.
divided by 1,000. That's correct, 0.19. And you want to do at most, so we have 0.19 here, right? So we're doing now 0.19 again is somewhere on my left, somewhere over here. This is where 0.19 is going to be.
Okay.
So now we want at most that number. So 0.19 is the most. And so if 0.19 is the most,
When E
we're looking
negative
at
E.
this. That's right. So when you do it, you're going to write this. You're going to say, and I'll write this more properly this time. P of this is going to be P of, right, P of P hat. Very good. P of P hat. P hat less than 0.19.
Awesome.
I think she's cooking with gas, ladies and gentlemen. 0.19. She got it now. I think she's on
Yeah,
it.
now, yeah, they're going. The variants are
This
going.
is equal to normal CDF, and this looks like something you did in the previous sections. This is now negative E99. Remember, you're plugging and you're not converting to a z-score first. It's not necessary. So you have 0.19. Your mean is 0.25. So this is 0.25, and use your 4 decimal places for your calculation. So this is 0.0137.
Perfect. And then
And
sigma.
And then you
0.
just, so now we're going to get our calculator. And we're going to say, let's clear this mess. All right, we have second distribution. Normal CDF. This is negative E99. Remember, use your toggle minus down here by the enter key. Second EE. 99. We're going to go to 0.19. We're going to have 0.25. We're going to have 0.0137. And we're going to get this thing with a negative 6. So not quite so small, but it's point. We're going to have 5 zeros. 1, 2, 3, 4, 5. And 5, 9, 5. Okay. So again, if we're going to 4, still negligible. Okay. We're not quite as far out in the desert as we were with the 0.33, but we're still out there. So if we rounded this to 4, this would be 0. If we rounded this to 6, we would get 0.000006 if you rounded to 6 places. But if you round it to 4, you get 0, essentially. So here, this is equal to 0.0000. If you round it to 4 places, it's 0%, roughly 0, right? 0%. Because it's so small. Now, most of the questions are not that small. Most of them are not. That's another reason why I wanted to do this one, because this one has extremely small percentages, but you do it the same way. Now, I'm
Gotcha.
not going to be able to help you finish number 2, but I want to show you here. Let's just set this up. Okay, now the campaign manager for a political candidate claims that 55% of registered voters favor the candidate over her strongest opponent. Okay, a simple random sample of 300 voters was selected to collect information on whether they favor the candidate over her strongest opponent. Are the conditions necessary to apply the CLT satisfied? All right, so what do they give me before I start looking at the bottom of this, right? What did they give me at the top?
The sample proportion? The 55?
No,
like,
they gave, this is the population proportion here. This doesn't say that it goes with 100, does it? Or I'm sorry, with the 300 voters, does it? This doesn't say 55% of the sample. This says 55% of registered voters. This is your P here.
sorry, I can't see your screen.
Oh, my apologies. Let me fix that for you. You probably can see something on my screen, but it's not what you should be seeing. Okay, how about now?
Yes.
Better? Thank you so much. So here you have, this is your P, because this is registered voters. This isn't my sample. This is my whole group.
Okay.
This is my population. This is my sample. N. This is my N.
Sample.
That's my sample size, right? After you get through A and B, the conditions, right? After you prove all that, when you get to here, when you get to C, it says, what is the probability that in a simple random sample of 300, less than 150? Now, how did they give you did they give you a proportion here?
150.
Okay, but that's not a proportion by itself. That's an X, right? So your proportion here now, this is going to be your sample. Why do I know that? Because look.
Sample.
In a sample of 300 voters, they're talking about that 300 voters up there, less than 150. So your P hat here, because that's my sample proportion, right? Remember, this is X over N. You see? So this is going to give me
Yeah.
150. I'm sorry, what was that?
Oh, never mind. I'm doing it with the old problem, 1,000. 150 divided
over 300. Should be 0.5.
by 5. There we go.
Yeah, that's better. So P hat is 0.5 and Q hat is 0.5. But when you test your assumptions, you're going to use this
Okay.
55, okay? So that's how it works. Okay.
Okay.
Think you can do it now?
Give me one quick second. Let me,
Take your time.
so 1 second. So once I have the 0.5, I'm gonna put it into the normal CDF.
Well, remember, you'll have to get the sigma of p hat first, remember?
Yeah, sigma of P.
So you have to, because you haven't done B, so you're not going to be able to do C. I just wanted to point that out to you.
But eventually I would do that, right? Like put
Yes.
it in the normal.
Uh-huh.
Okay,
Yeah.
okay, I think I can do it.
Yeah, it's just like, so I won't leave you behind, but I'm going to stop recording.